Hello, Math Study students. In this lesson, we're going to begin our study of logic. We'll be taking a look at 9.1 through 9.5 today, and we're going to start with statements and connectives. The building blocks of logic, we need to start with some statements. Later, we'll talk about how to join those statements together with connectives, and then study the logic or the truthness of those statements. So let's start with what a statement is. A statement is a phrase or a sentence that must have a precise mathematical meaning, and it has a truth value of true or false, but not both. Okay, now we're talking about mathematical statements with mathematical meanings. A statement in math or in logic, which is both true and false, would be a logical contradiction. Now, in everyday conversational language, you might have a statement that has some truth to it and some not, or some falseness to it. But in mathematical logic, every statement is either true or false. It can't be both. So let's look at these and determine which of these are statements. And by statements, we mean a statement that would have a mathematical meaning and can be assigned a truth value. So, for example, prime numbers are greater than 1. Well, that has a precise mathematical meaning. So yes, it is a statement, and let's assign it a truth value. That statement is true. All prime numbers are greater than 1. How about this next statement? 2 plus 2 equals 5. Well, that has a precise mathematical meaning. So yes, it is a statement, but when we assign its truth value, it's definitely false. I hope you agree with that. Okay, the next one. Is it Monday? Well, that's not a statement. That's a question. We can't really assign a truth, any kind of truth value to it. The same thing with number 4. Make some noise. You see that on the big screens at professional ball games. That doesn't have a precise mathematical meanings. We can't assign it a truth value, so we'll say it's not a statement. How about number 5? Every square is a rectangle. Has definite mathematical meaning. So yes, it is a statement, and we can assign a truth value to it. Every square is a rectangle. So we'll say that that is true. Now, a compound statement is made up of simple statements joined together by what we call a connective. And there are 5 commonly used connectives, and let's take a look at those and look at their symbols. Okay, so the first connective is the word not. That connective is what we call a negation. Okay, and the symbol that we're going to use for a negation might be different than what you've used in the past. It kind of looks like this. It looks like a little right angle. So kind of a right angle with a long side and a short side. Okay, so when you negate a statement, you either add the word not, or you take the word not away, or you state the opposite meaning. So for example, if you have a phrase that would have exactly one opposite meaning, like the student was absent today, we can either write the negation by saying the student was not absent today, or state the opposite meaning, which would be the student is present today. You'll see some examples like that later. Okay, the next connective is and. That is what we call a conjunction. So when you join two statements with the word and, it's a conjunction. The symbol we use for joining two statements will look like this. Okay. And then you see the word or twice here because there's 2 different uses of the word or. When you use the word or to join two statements, that's called a disjunction. And there are 2 different kinds of disjunctions. We'll look at some examples in a minute. The first one is called an inclusive disjunction. We'll talk about what that is in just a minute, but for right now, let's just learn the symbol. The symbol, you take the symbol for a conjunction and turn it upside down. The other use of the word or is what we call an exclusive disjunction. Exclusive disjunction. Okay, and that symbol looks like that. It's the disjunction symbol with a bar underneath it. Okay, and then our last connective is an if-then statement. That's when you have one statement that implies another statement. You'll remember those from geometry. So we call this an implication. And the symbol we use for an implication is an arrow. So when we have one statement that implies another one, we say the first statement, put the arrow implies the second statement. So let's talk about what we mean by these two versions of or. Now, what we're talking about for now is just an everyday conversation, okay? When you use an everyday conversation, when you use the inclusive or, the implied meaning is one or the other. Okay, so one or the other, or both. Now, in a few minutes, when we start talking about math logic, okay, we have to be very precise. So in math logic, the word or used alone, is always assumed to be inclusive, but that may or may not be true in everyday conversation. Like this example. In everyday conversation, if you say you may study study Spanish or French as part of the IB diploma, that's an inclusive or, because a student could study Spanish alone or French alone, or some students might study Spanish and French, okay? So in everyday conversation, you can use the word or, and it is implied to be the inclusive use of or. Okay, the exclusive use of or in everyday English, the implied meaning is one or the other, but not both. So one or the other, but not both. Now, in math logic, if you want to use the exclusive or, then you will have to add a phrase. The exclusive version of or must include the phrase but not both in math logic. However, we'll see in an example here that it could be implied, okay, in everyday conversation. So, for example, you may study mathematics HL or mathematics SL. Now, I wouldn't even need to include this phrase in the IB diploma because it's common knowledge that you couldn't be in both HL and SL mathematics. That just can't happen. So this phrase would not even need to be here, and the exclusive or would be implied. So let's look at some examples and determine whether these statements is an inclusive or exclusive use disjunction, and we're just talking about an everyday conversation. So number one, a coin when flipped lands on either heads or tails. Well, what's implied there? Can a coin land on both at the same time? No, it has to be one or the other. So that's in everyday English an exclusive use of the word or. Okay, how about number two? You may choose fries or salad with your meal. Well, do you suppose some people want both? They could have fries and salad. So in everyday English, that's probably the inclusive use of the word or. If you want to be more precise, if you can only choose one, you'd want to add that phrase, but not both, okay? How about this one? A student can play basketball or football. Well, do you know anybody that plays both? So that's not, again, in everyday English, I think it's commonly understood that a student could play both basketball and football. Okay, and then number four, the test will be on Tuesday or Wednesday. Well, the test can either be one day or the other day. You're not going to have a test on both days. So again, common knowledge or just in everyday conversation, we would see how that's the exclusive use of the word or. Okay, so that's for everyday English. Now, as we said, when we get into more math logic and in your homework, if you are talking about logically, the logic use of the inclusive or, okay, if you see or alone, it will always assume to be inclusive. If you want to use the exclusive use of or in math logic, you have to add that phrase, but not both. So let's summarize the use of these connectives. We're going to look at, again, the words we use, the symbols we use, how they correspond to set theory, okay, how you would represent them in a Venn diagram, and then we're going to talk about truth tables and how you can indicate the truth value of a compound statement. So let's start with, first of all, with the negation. The language you use is usually the word not, although sometimes you'll see where you can use a word that has the opposite meaning, the opposite truth value. The symbol we use for a negation, as we said earlier, is this little kind of right angle looking thing. Okay, now the corresponding set theory operation would be the complement that we've talked about. Okay, so in this Venn diagram, here is P, okay. How would we indicate not P? The negation of that would be everything that's outside of that P circle. So let's just go ahead and just shade that in. So not P would be everything outside of the P circle in the Venn diagram, okay? And then let's take a look at a truth table, and you've probably done these before. If I have a statement that has a precise mathematical meaning, it has one of two truth values. That statement P can either be true or it can be false, okay? Now, let's talk about the truth value of not P. Well, if you negate a statement, it should have the opposite truth value. So if a statement is true, its negation should be false, and if a statement is false, its negation should be true. Okay, so now let's take a look at a conjunction. The word you'll see, the language we use when we're using a conjunction will be the word and. The symbol is the caret symbol. And in set theory, a conjunction would be represented by an intersection. Okay, remember how we define intersection? If we want to talk about the intersections of sets P and Q, those would be the elements that are in both P and Q at the same time. So we would shade this in. Okay, so let me shade that. Okay, now let's talk about a truth value of, this time we're going to come up with a truth value for a conjunction. So a conjunction is made up of two statements. So let's look at all the combinations of truth values for P and Q. Well, P could be true and Q could be true. Or P could be true when Q is false, or Q could be false when Q is true, and then the last possibility is if they're both false. Okay, so now, when would a statement be true? When would a conjunction be true? Well, a conjunction is only going to be true when both parts are true at the same time. An element is only in the intersection of two sets if it's in both sets at the same time. So, for example, these elements are not in the intersection. These elements are not in the intersection that are Q only. And the elements out here that are in neither P or Q would also not be in the intersection. So the only time a conjunction is true is when both statements are true. And then all other conjunctions are logically considered to be false. Okay? Now, let's look at our two uses of the word or. Okay, the inclusive disjunction, again, the word we use is or, okay? The symbol we use is an upside down caret, and the set theory operation that would coincide with that would be the union of two sets. Remember, an element is in the union of two sets if it's in one set or the other or both, okay? So if I want to indicate P or Q in this Venn diagram, I'm indicating the union. So that's everything that's in one set or the other or both. So that would be P and Q and also the overlap. Okay, so now let's talk about truth value. Now let's go ahead and set up the same for the possibilities for P and Q. Let's just follow this pattern, both true, true, false, 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 true, or false, false. Okay, let's just use that same order every time. You don't have to use this order, but I would just to be consistent. Okay, so when is a disjunction false, an inclusive disjunction? Well, when is an element not in the union of two sets? The only time when an element is not in the union of two sets is when it's in neither set. Okay, so the only time that this statement is false is when both parts are false and all other disjunctions would be true. Okay, so then let's finish up with this, take a look at this exclusive disjunction. Okay, now, we use the word or, okay? If we're going to be precise and mathematically logic, we would also have to use the phrase, but not both. Okay, so one or the other, but not both. The symbol we use for that is the disjunction symbol with a bar underneath it. And the set theory operation is something that we call a symmetric difference. Symmetric difference. So I think a picture of that is the best way to understand it. If we want to shade in an element that's in one or the other but not both, we'd shade this part and this part, and we would leave the intersection empty. So it's going to look like this. Shade P, shade Q, but do not shade the intersection. Okay, so let's talk about the truth value of of a disjunction using the exclusive use of the word or. So let's look at our two parts of our disjunction. P could be true and Q could be true. P could be true and Q could be false. P could be false and Q could be true, or they could both be false. So let's use the Venn diagram to determine when this disjunction would be true. Well, an element is in P or Q but not both if P is true and Q is not true. So if an element is in P but not in Q, it's in this inclusive disjunction, or what we call the symmetric difference. So when P is true and Q is false, that's a true statement. An element is in the symmetric difference if it's here. So that's when you're in Q but not in P. So when P is false and Q is true, then that exclusive disjunction would be true. So when would it be false? Well, it's going to be false if an element is in the intersection. Okay, so if both P and Q are true, okay, then it's in this unshaded part. So if P and Q are both true, then the exclusive disjunction is going to be false, because remember, it's P or Q, but not both, okay? And then the other time it would be false is an element out here that's in neither P nor Q. So if both parts are false, the exclusive disjunction is false. Okay, so we'll be doing some problems in class to help you kind of solidify these concepts. And if you have any questions, you can ask me then.